Hello everyone, I welcome you all once again to MSP lecture series on interpretive spectroscopy. This is the 11th lecture in the series. In my previous lecture, I had initiated discussion on 31p NMR spectroscopy, and also I was telling you how simple it is to understand if you decouple, if you have a large number of protons or hydrogen atoms, and 13C and 31p, they can always simplify it by irradiating and avoiding interaction of those nuclei with hydrogen atoms, so that it is further simplified and interpretation would be very easy. In the same way, often we do it in case of phosphorus NMR also. And let me now continue from where I had stopped, and now let us look into the extensive list of chemical shift range for various groups shown here in the slide. And you can see here, in case of primary phosphine, where we have one alkyl aryl group on phosphorus and two hydrogen atoms are there, the range will be -150 to -120. That means they are highly shielded. And then if you have secondary phosphine, where we have two alkyl aryl groups and one hydrogen is there, it comes down, it will be around -100 to 80 ppm. And then if you go to tertiary phosphine, whether it is alkyl or aryl, tertiary phosphine show in the range of -60 to -10. And in case of secondary phosphine, if we have halogens in place of hydrogens, so it comes around 80 to 150. So it is slowly moving from shielded to deshielded region as we are adding more electron withdrawing groups on phosphorus. That can be clearly seen from these trends of chemical shifts here. And if you take NR2 groups are there on phosphorus amides, in that case it comes to 115 to 130 ppm. And if you have phosphides, trialkoxy or triaryloxy phosphides, we can see the chemical shift coming in the range of 125 to 145. And if O is replaced by S, thiophosphides, chemical shift range remains more or less same. It is 110 to 120. And if you have trihalophosphines like trichlorophosphine, tribromophosphine, the chemical shift range is about 120 to 225. And then if you have two aryloxy groups and then one halogen, again it is further comes to downfield and around 140 to 190. And then if you have two halogen atoms on phosphorus with one carbon, it comes to 160 to 200. And then if you have a combination of carbon, halogen and nitrogen, it further comes to downfield to 165 to 185. And then if you have pentavalent tetracoordinated compounds like POCl3, the range is -8 to 5. And in case of, again we have a combination of halogen and alkoxide or aryl oxide, it comes to -30 to 15. And then if you consider here the same combination with variation in the halogen and alkoxy or aryloxy group OR groups, then it can fall down to -20 to 25. And then for a typical phosphate, it comes around -20 to 0. And then again we can have among pentavalent compounds, tetracoordinated one with sulfur P double bond S, it comes in the range of 60 to 75. And then if you have this kind of compound, it comes to -5 to 7 OR group and C, it can be alkyl. And then we have with OR group and S, it comes around 80 to 110. And then in case of this one, we have hydroxy groups are there with one carbon, it comes in the range of -5 to 25. And then here it comes between 0 to 20. And then if you have OR group and two CP groups are there and PO, and then it comes around 0 to 60. And again two halogens are there and one carbon, it comes around 5 to 70. And then halogen and nitrogen, it comes around 25 to 50. And then if you have whether PO or PS compound with C3, it comes in the range of 20 to 60. That means thiophosphine oxide or phosphine oxide with tertiary phosphine oxide or tertiary phosphine thioxide, they come in the range of 20 to 60. And if you have halogen, R2POCl comes around 40 to 90. And If you have penta-coordinated pentavalent phosphorus compounds, it comes around -75 to -5. And if you have phosphonium salt, it comes around -5 to 30. And if you have Wittig reagents, they come around 5 to 25. And then if we look into phosphines, trimethyl phosphine shows at -62, triethyl phosphine at -20, triisopropyl -33, triisopropyl is normal propyl it is 33, and isopropyl is -19.4, and tri-N-butyl phosphine normal one will be 32, and isobutyl is -45.3, and secondary butyl is 7.9, and tertiary butyl is 63. So most of these phosphines we use with palladium or platinum in combination, or with rhodium while using them in homogeneous catalysis. From that point of view, just having some knowledge about their chemical shift would be very helpful. Phosphorus 5 compounds, if you look into it, trimethyl phosphenoxide 36.2, triethyl phosphenoxide comes at 48.3. And then if you look into phosphonium species cation, it comes around 24.4, and phosphate comes around 6, and PF5 comes around -80.3, and PCl5 -80, and MEPF4 comes around -29.9, and Me3PF2 comes around -158. So further some more compounds are there. When you have difluoromethylphosphine comes around 245, much more de-shielded. And then if you have methyl phosphine comes around -163.5, and then if you have methyl dichlorophosphine 192, and dibromomethylphosphine 184, dimethyl fluorophosphine 186, dimethyl phosphine is 99, dimethyl chlorophosphine is 96.5, dimethyl bromophosphine is 90.5. Again here trimethyl phosphine sulfide is 59.1, triethyl phosphine sulfide is 54.5, and tetraethyl phosphonium salt comes around 40.1, and then if you have PS3 minus, it comes around 87, and PF6 comes around 145. And this PF is very, very important, because in most of the metal complexes we use anion, a larger anion such as hexafluorophosphate, and the phosphorus chemical shift comes around 145. This comes as a something like this. As a septate because of coupling with 6 fluorine atoms, whereas 19F NMR would show a simple doublet, something like this. And PCl4 cation shows at 86, and PCl6 anion shows at -295, and it shows at 8.0. I have covered most of the compounds we come across as far as phosphorus compounds are concerned. Now let us look into very interesting examples here. I have taken one example of 2,6,7-trioxa-1,4-diphospho-bicyclo-2,2,2-octane, something like this. The structure is also shown here. And if you just look into the spectrum, this is phosphorus proton decoupled spectrum, whereas this one is coupled spectrum. Shows two singlets. I have labeled as alpha and beta. Two signals are there. Both of them appear like septates, having 7 lines are there. And where the 7 lines are coming from? In the coupled spectrum, if you just look into it, you see two separate septates with different spacings. The moment you look at the spacings, you should be able to assign without any hesitation that this is for P alpha and this is for P beta. Because if we consider hydrogen atoms, this is 1-2 bond coupling is there in this case. 2J pH coupling is 8.9 Hertz, whereas here what happens here 1-2-3 bond coupling is there here. 3 bond coupling magnitude will be much smaller as a result. And how the 7 lines, you can consider 2, 2 to 6 are there, and all of them are equivalent. When they are equivalent, they can be considered as one type of nuclei. As a result, again you use 2Ni plus 1 rule here, 2, and number of such identical hydrogens are 6, spin half plus 1 gives 7 lines. 7 lines are seen here. So sometime if we have difficulty in assigning the chemical shift, because both of them in the decoupled one are showing singlets, and we may have difficulty in assigning the signals, whether this is P alpha or whether this is P beta or something like that. In that case, if we record the coupled one, that can help us in identifying without any ambiguity. So this is the advantage of recording. Coupled one is for understanding, decoupled one for simplification. Wherever simplification is needed, we can go for decoupled spectrum. Wherever we want more information to have better understanding of the molecule and interpretation, then we should go for coupling, something like this. The stronger coupling of P beta, because there are only 2 bonds separating them, okay, and then the values are also given here. You can see here, okay, 8.9 hertz, and then this is 2.6 hertz. I hope now you have understood how easy it is to interpret 31p NMR spectrum, both in the decoupled as well as the coupled one. Okay, so now let us look into 1H NMR spectrum of the same molecule here. If 1H NMR, if you look into it, let me write the structure again. So now this is alpha and this is beta we are calling, and then now if you look into 1H NMR, all are identical and they couple differently to 2 phosphorus atoms, alpha phosphorus and beta phosphorus. And then since beta phosphorus is close to hydrogen, 1-2 bond coupling, first it will split into a doublet like this. This is 2J PCH, and now this P alpha, it is 3 bonds away, and this will be 2.6. So at the end what we get is a doublet of doublet. So that means when we combine the information obtained from 2 different type of spectra, we should be able to interpret and understand without any problem. And sometimes you can also add data obtained from IR and UV if needed, and also from mass spectrometry. So then what happens if we oxidize this compound? Now it is a trivalent phosphorus compound. We can oxidize. When we are oxidizing, we can make it P double bond O or P double bond S. And here when X is, actually when it is oxidized, it is labeled as Y and X. And then when X and Y, we can consider when X is O and Y is O, both of them are oxides. In that case what happens? It comes around minus 18.1 and 6.4. And when both are lone pairs and XY are lone pairs, that is trivalent phosphorus, in that case alpha comes at 90 ppm and beta comes at minus 67 ppm. So this information directly comes from the coupled 1H NMR spectrum. And then if we replace, if we oxidize both the phosphorus with oxygen, then P alpha comes at minus 18.1 and then beta comes at 6.4. But if we oxidize with sulfur and get corresponding disulfide, then P alpha comes around 51.8, whereas P beta comes around minus 70.6. This is still lone pair is intact. Only P alpha is oxidized to sulfur and still P beta has lone pair intact. In that case, slight shift is there. You can see minus 67 to this one coming. It's because of secondary effect, you will see, because other phosphorus is now oxidized. So it comes around 51.8, and this is because little bit alteration in the neighboring groups can also have some influence on their chemical shift, can be seen from this example here. Let us look into one more example here. This is a very interesting molecule. We have one ethoxy group is there on phosphorus and we have CF groups are there. First let us look into the 19F NMR. 19F I haven't discussed it. 19F is also very similar to 31P and 1H NMR because it's also the spin is half and it is 100% abundant. The interpretation is very similar to 1H and very similar to 31P NMR. So that's the reason I am considering this molecule where we have phosphorus as well as carbon. Now first look into 19F NMR of this molecule here. When we look into 19F NMR of this one, both of them are identical. CF3 identical. They are coupled through 2 bond to phosphorus. So one phosphorus is there. So this signal will be split into doublet, and here this 2J PF coupling is about 86.6 hertz here. But when we look into phosphorus NMR, phosphorus NMR, and phosphorus NMR is here 1H decoupled 31P NMR. In this one, since these two are identical, 6 fluorine atoms together split this phosphorus signal into a septate. You can see here 7 lines are there. And of course, one can also look into 1H NMR. So of course, 1H NMR we had discussed plenty of example, it's not needed. So one can clearly see how simple to interpret data obtained from 19F, 13C and also 31P NMR. Let us look into a few more interesting molecules. Now let us look into another phosphorus compound here. where we have direct phosphorus to hydrogen bond is there and 2 OMe groups are there. Just for convenience of interpretation, I have expanded on only one of them. Now, if we look into 31p NMR spectrum, it shows a doublet with pH coupling of 715 Hertz here. This is 1J coupling. Usually 1J phosphorus hydrogen couplings are very large. They can go to as high as 1200, and 500 to 600 is very common. In this case, we are seeing the coupling of 715 Hertz. And then when we look into 1H NMR, in 1H NMR what happens, we have two different type of protons are there. One is H directly attached to phosphorus and another one is OCH3, and OCH3 is 1, 2, 3 bond apart, so it can show a doublet with phosphorus. So this is the one. So here we can see 1, 2, 3 bond coupling is there. So 3JPH is observed in this case. Whereas in this one, when we look into 1H NMR, the magnitude of this coupling should be same what we observed here. We are observing here, this is 1J coupling, this is 715 Hertz. So that way, if we have again some ambiguity about the coupling constants, we can verify the coupling constant value by going to NMR of other nuclei. So now we have understood that the interpretation is very similar, but 31p sample preparation is also very similar to 1H sample preparation. As in other NMR experiments, 31p NMR sample must be free of particulate matter because of homogeneity problem and other things. Always if any particulate matter is there, it is better to filter and then use clear solution. A reasonable concentration of 2 to 10 milligrams of sample dissolved in about 0.6 to 1 ml of solvent. If needed, the solution can be filtered through Silite to remove any suspended particles. Anyway, the solid will not analyze in the NMR spectrum, but they can create problem about homogeneity, and that results in broadening of the signals. Unlike 1H NMR, no need to dissolve in a deuterated solvent, since common solvents do not have 31p NMR nuclei to contribute to spectra. So that is the major advantage here. Most of the deuterated solvents are very expensive, and also we are not using an internal standard as well. So we are using an external standard, that is 85% phosphoric acid, that is taken in a capillary tube. That capillary tube can be inserted into the NMR tube, and also you can do external locking, so we can use any solvent without any problem. That saves a lot of money. So from that point of view, again, phosphorus NMR is much simpler and much easy, much economical. And one should not try to obtain 1H NMR spectrum from the same sample taken in common solvent. That is the thing. After taking phosphorus NMR, if we want to understand the proton signals, we should not use the same solvent if we have not used a deuterated solvent. So from this point of view, if you want to use the same sample for recording, say 31p, 1H, 19F and 13C, all those things, then it is better to dissolve in a deuterated solvent in which phosphorus compound is highly soluble and gives a clear solution. Since it is possible to use non-deuterated solvents, 31p NMR offers many advantages such as assaying purity readily, and also one can monitor progress of reaction. For example, to understand the mechanistic aspects, when we are doing reaction, in the continuous reaction, it comes very handy. So this is the major advantage. That's the reason variable temperature 31p NMR is extensively used in understanding the mechanism and also to trace the nature of the intermediates. This is quite helpful. Okay. So let me stop here and take few more very interesting spectra in my next lecture. Until then, have an excellent time reading about NMR spectroscopy. Thank you.